Right now at CERN, scientists hold a speck of antimatter and ask a question that sounds insane. When they let go, will it fall down like a stone or drift up toward the sky? You will meet the ghost twin of every atom in your body, a particle that flips gravity's sign and the tower where antimatter was finally dropped. If wonder like this keeps you curious, a quick like or subscribe helps this channel grow. Prepare yourself. We begin. Picture a scientist standing over a sealed steel chamber, holding the strangest sample ever made. Inside floats a tiny cloud of antimatter, a handful of atoms that are the exact opposite of the atoms in your hand. Same size, same shape, opposite in every charge. Now she does something that has never worked before in all of history. She lets go, and for one heartbeat nobody in the room knows which way it will move. Everything you have ever dropped falls down. A coin, a phone, a raindrop, a sheet of snow sliding off a roof. Down, always down. The earth pulls, and matter obeys. You expect antimatter to obey the same pull. But antimatter is the great rebel of physics. It carries the opposite electric charge of ordinary matter. Where an electron is negative, its antimatter twin is positive. Where a proton is positive, its twin is negative. Antimatter breaks the mirror of the world at every level we can measure. So a wild idea crept into the minds of serious physicists. If antimatter flips charge, could it flip gravity too? Could a speck of it, released in that chamber, drift upward toward the ceiling while everything else in the universe sinks? That single possibility is one of the most dangerous questions in modern science. If antimatter fell upward, even a little, it would tear open the deepest law we have about how reality holds together. For most of the last century, the honest answer was 3 quiet words. We do not know. The question was enormous. Scientists ached to solve it. They simply could not catch enough antimatter, hold it still enough, and shield it from every stray force long enough to watch a single speck fall. Imagine trying to weigh a snowflake in the middle of a hurricane. The snowflake is real. It has weight. But the wind screaming past you is a billion times stronger than the faint tug you're trying to measure. Every attempt gets torn away before it starts. Gravity is that snowflake. It is the weakest force in all of nature by a staggering margin, and antimatter is the most fragile stuff that exists, gone in a blink if it so much as brushes the wall of its container. So the chamber, the sample, the moment of release, all of it took decades of invention just to become possible. And when that moment finally arrived, in a laboratory buried under the border of Switzerland and France, the people who built the experiment were openly divided. Some felt certain the antimatter would sink like every stone before it. A few, quietly, wondered if they were about to witness a piece of the universe choose to rise. The disagreement inside that laboratory was real, and it had waited almost a century for an answer. The stakes reached far past one falling atom. Hidden inside this question sat a suspect for the greatest disappearance in the history of everything. Almost all the antimatter that should exist has vanished from the cosmos, unaccounted for. Some physicists believed that if antimatter fell the wrong way, it might finally explain why. To see how a single dropped atom could carry that much weight, we have to travel back to the man who dreamed antimatter into being before a single piece of it had ever been seen. Here is the strange part. We measured almost everything about antimatter to a precision that borders on the absurd and still had no idea which way it fell. Take a positron, the antimatter twin of the electron. Physicists have pinned down its magnetism to more than 10 decimal places. That is like measuring the distance from New York to Los Angeles and being sure of the answer down to the width of a single human hair. They know its charge. They know its mass. They can predict how it spins in a magnetic field with breathtaking accuracy. Then there is the antiproton, the heavy anti-twin sitting at the center of an anti-atom. Scientists trapped single antiprotons and compared them to ordinary protons with insane care. The two matched in mass to better than 1 part in a billion. Flip a proton into its opposite, and its weight stays identical to a level that would make a jeweler weep. So we had a full portrait of antimatter, its electric personality, its spin, its magnetic soul, all catalogued in exquisite detail. Every column in the ledger filled in with numbers of extraordinary confidence. Every column but one. The column for gravity sat completely blank. After nearly 90 years of study, The simplest childhood question you could ask about any object, does it fall, had no direct answer for antimatter. A curious 8-year-old dropping a spoon knew more about how their spoon behaves than the finest laboratories on Earth knew about a falling antiatom. That gap was a gaping hole in the foundation of the whole field. We built entire theories assuming antimatter falls exactly like matter, and we plugged that assumption into our picture of the early universe, our models of stars, our understanding of the Big Bang. All of it rested on a guess that no one had ever tested by simply letting the stuff go and watching. Think of a bridge engineer who has calculated every bolt, every cable, every rivet, and knows each one to 1,000th of an inch. Then someone asks a simple question. Have you checked that the ground under the bridge is solid? And the engineer goes pale, because the answer is no. Everything sits on top of that untested ground. Gravity was the untested ground under antimatter physics. Most scientists were confident it would hold. Confidence is not the same as proof, and the whole point of an experiment is to force nature to answer instead of assuming she agrees with you. Nature has humbled confident physicists many times before, and nobody wanted to become the next cautionary tale. The problem was fiendish. To weigh how antimatter falls, you need it neutral, still, cold, and shielded from forces trillions of times stronger than the gentle pull you want to see. For decades that recipe read like a fantasy. Yet the reward for cracking it kept scientists awake. Because a real answer might do more than fill in a blank column. It might explain why the universe is built almost entirely from matter, with its opposite twin nearly wiped from existence. To understand why anyone dared to dream that antimatter might rise instead of fall, we have to meet the quiet genius who conjured antimatter out of pure mathematics years before anyone believed him. In the late 1920s, a shy young Englishman sat scribbling equations that would rewrite what reality is allowed to contain. His name was Paul Dirac, and he spoke so rarely that colleagues joked his personal unit of conversation was 1 word per hour. What he lacked in speech he made up for in a strange, almost musical faith in mathematics. He believed that if an equation was beautiful enough, the universe would be forced to obey it. Dirac was trying to marry 2 of the greatest ideas in physics: Einstein's rules for things moving near the speed of light, and the brand new quantum rules that govern tiny particles like the electron. Nobody had made the 2 agree. Dirac wanted an equation that captured both at once. After a long struggle, he found one. It was elegant, compact, and it described the electron perfectly. It predicted the electron's spin, a property earlier physicists had bolted on by hand as a natural consequence of the math. It was a triumph. Then the equation did something that terrified him. It had 2 sets of answers. One described the ordinary electron with its familiar negative charge. The other described something with the same mass, moving as if it carried positive charge instead. The math insisted this second solution was real. It sat right there in the equation, refusing to vanish. At first, Dirac tried to explain it away. Maybe the second solution was just the proton, the only positive particle anyone knew about at the time, but the numbers said no. The mystery twin had to weigh exactly what the electron weighed, and the proton is nearly 2,000 times heavier. The math had conjured a particle that had never been seen by anyone, anywhere. Imagine solving a simple puzzle about how a coin spins, and having your correct answer insist that a second, invisible coin must also exist, identical in every way, yet somehow inside out. You did not ask for it. You cannot delete it. It falls out of the logic whether you like it or not. Dirac finally took the terrifying step. In 1931, he proposed that the second solution described a real particle, a twin of the electron with opposite charge. He called it an anti-electron, a member of a whole new category of stuff that would come to be known as antimatter. This was a leap of pure nerve. He was predicting an entire shadow world, built from mathematics alone, with 0 evidence that any of it existed. Many physicists thought he had wandered off the edge of sanity. Predicting a particle nobody had ever detected on the strength of a symmetry in an equation felt reckless. Dirac held his ground. He trusted the beauty of the math more than he trusted the doubts of his peers. If the equation demanded a mirror twin for the electron, then the universe, somewhere, had to be making them. He had handed the world one of the boldest bets in the history of science. Either the anti-electron was out there waiting to be found, or one of the most elegant equations ever written was quietly lying. The bet would not stay a bet for long. 1,500 miles away, high on a mountaintop, a young experimenter was about to point his camera at the sky and catch a streak of something impossible curving through his detector. On a cold mountain in California, a physicist named Carl Anderson was hunting for particles raining down from space. He had built a cloud chamber, a sealed box of cold vapor where a passing charged particle leaves a thin trail, like the white line a jet scratches across a blue sky. Wrap that chamber in a strong magnet, and the trails curve. Positive particles bend one way, negative particles bend the other. The tighter the curl, the lighter and faster the particle. Anderson was photographing cosmic rays, high-energy particles born in the violence of distant stars slamming into the top of our atmosphere and shattering into showers of debris. Night after night his camera captured streak after streak. Then, in 1932, one photograph stopped him cold. A track sliced through his chamber, curving in a way that made no sense. It bent like a positive particle, so it should have been heavy, like a proton. But the trail was too thin and too gently curved for something that heavy. It moved like a feather-light electron, yet it curled the opposite way from every electron he had ever recorded. A lightweight particle, with positive charge. Anderson stared at a photograph of a thing that, according to all known matter, had no right to be there. To make sure the particle was moving the direction he thought, he had slipped a thin lead plate across the middle of the chamber. A particle punching through the plate loses energy and curls tighter on the far side. That let him read which way it travelled. The reading was clear. This was a light positive particle, exactly the anti-electron Dirac's equation had demanded from thin air. Anderson gave it a name that stuck: the positron, the first piece of antimatter ever seen by human eyes. Think of it like this. A famous author writes a novel and casually mentions a rare bird that no naturalist has ever recorded, a bird that logically must exist to complete the story. Everyone assumes he invented it. Years later, a photographer on a mountain snaps a picture of that exact bird, feathers and all. The impossible creature was flying above us the whole time. That is what Anderson caught. Dirac had drawn the bird from mathematics. Anderson had photographed it in the wild. The shy man's reckless bet had paid off completely. Antimatter was real. It existed. It came streaking out of the sky and left its fingerprint on a photographic plate. Within a few years, physicists confirmed the pattern held for other particles too. Every kind of matter, it seemed, had a mirror twin waiting on the other side. And with antimatter proven, a fresh set of questions rushed in behind it. If this stuff carried opposite charge, how far did the mirror go? Did it obey the same clocks, the same forces, the same rules? Did it feel the pull of the earth the way our matter does? That last question turned out to be the hardest of all. Charge was easy to test. You watch which way a particle bends in a magnet and you know its charge in an instant. Gravity refused to cooperate. It is so faint that a magnet can hide it completely, drowning the whisper of falling in a roar of electric force. Before anyone could dream of dropping antimatter, they had to understand exactly what it would mean for a piece of it to rise. And the answer is far stranger than a balloon floating to the ceiling. To fall upward, antimatter would need something no object on Earth has ever had. Weight that pushes away instead of pulling in. We toss around the phrase falling up too casually. A helium balloon rises, and we call that falling up, but it is a trick. The balloon still has ordinary weight. The Earth still pulls it down. Air simply shoves it aside because the air around it is heavier and sinks below it, forcing the light balloon upward. Take away the air, and the balloon drops like everything else. Its weight was always positive. It was riding on a crowd. True anti-gravity would be something else entirely. It would mean antimatter has negative gravitational mass. Its very weight would point the wrong way. Set it in empty space near the Earth, with no air, no wind, no trick, and it would drift away from the planet on its own, repelled by the same pull that anchors you to your chair. Sit with how bizarre that is. Every object you have ever touched pulls toward every other object. The Earth pulls the moon, the sun pulls the Earth. Your body, faintly, pulls on the walls of the room around you. Gravity in our universe only ever attracts. It has one direction, always inward, always together. In 14 billion years, nobody has ever seen a scrap of matter that pushes away by gravity alone. Negative gravitational mass would break that unbroken rule. And it would do far weirder things than simply float. Imagine a chunk of ordinary matter sitting next to a chunk of this anti-gravity antimatter. The normal matter pulls the strange stuff toward it, the way it pulls everything, but the strange stuff pushes the normal matter away, so one runs toward and the other runs from. They would take off together, accelerating across the room forever, one chasing and one fleeing, gaining speed out of nowhere. A pair like that would look like it was creating energy from nothing, which nature almost never allows. Picture two dancers holding hands. One wants to pull close, the other wants to push apart. If both got their wish at once, they would go spinning off across the floor faster and faster, never stopping, powered by a contradiction. That runaway is exactly the nightmare physicists saw when they imagined anti-gravity. This is why most scientists felt in their bones that antimatter had to fall down. Falling up seemed to lead straight to absurdity, to machines that pull energy from empty space, to a universe that leaks power for free. The tidy rules of physics recoiled from it, yet the door never fully closed. A clever version of the idea whispered that maybe antimatter does not need pure negative weight to behave strangely. Maybe it falls down, but slightly slower. Maybe a faint extra push nudges it, a whisper of repulsion riding on top of ordinary gravity, too small to cause runaway madness but big enough to measure if you looked hard enough. That softer possibility was harder to laugh off. It did not obviously break the universe, it just added a tiny new ingredient, a subtle force that treated matter and antimatter differently in the one arena we had never checked. To know whether that whisper was real, scientists needed a rock-solid rule to test it against. A law so deep, so thoroughly confirmed, that any crack in it would shake physics to its roots. That law was about to arrive, and it came from a man dropping objects off a tower long before antimatter had a name. 400 years ago, a stubborn Italian is said to have climbed a leaning tower with two balls of different weight, ready to overturn 2,000 years of belief. For most of history, people trusted a simple idea handed down from the ancient Greeks. Heavier things fall faster. Drop a cannonball and a pebble, and surely the cannonball hits the ground first. It feels obvious. It also happens to be wrong. Galileo Galilei suspected the old wisdom was rotten. According to the legend, he dropped two balls of unequal weight from the Tower of Pisa and watched them strike the ground at the same instant. Whether or not he truly climbed that tower, he proved the point with careful experiments rolling balls down ramps, slowing the fall so he could time it. His conclusion shook the world. Strip away the drag of the air, and all objects fall at exactly the same rate. Feather or boulder, they drop together. The reason sounds like a paradox at first. A heavier object does feel a stronger pull, but a heavier object is also harder to move, more stubborn, more resistant to speeding up. The extra pull and the extra stubbornness cancel out perfectly, so everything accelerates downward at the same steady rate, no matter what it is made of. This became one of the most sacred rules in all of science. Physicists call it the universality of free fall. It says that gravity does not care what an object is. Iron, gold, glass, water, wood, all of it falls identically. Only the object's motion matters, never its ingredients. The most beautiful proof came not on Earth, but on the Moon. In 1971, an astronaut named David Scott stood on the grey lunar surface, where there is no air to slow anything down. In one hand he held a hammer, in the other a falcon feather. Millions watched as he let them go at the same moment. With no air to cheat, the hammer and the feather fell side by side and touched the dust together. A tool of metal and a wisp of a feather, landing as one. That single moment, broadcast from another world, showed the rule at its purest. In a place without air, the heaviest and the lightest fall in perfect step. Now hold that rule up against antimatter. Everything we know says an anti-atom should fall exactly like an ordinary atom, at the same rate, in the same direction, obeying the same universal rule that governs hammers and feathers and moons. Antimatter has mass. Mass falls. The law seems airtight, but there is a razor-thin gap in that reasoning. Every object Galileo dropped, every ball Scott held, was made of ordinary matter. The universality of freefall had been confirmed thousands of times, to staggering precision, using matter and only matter. Nobody had ever dropped its opposite. So the rule was really a promise about one half of the world. Matter falls the same regardless of its type. What if antimatter simply refused to join the club? What if the mirror world played by a different rule, one we never suspected because we had never tested a single mirror object? To turn that razor-thin gap into something a scientist could challenge, the falling rule needed to become something deeper. A cornerstone of the entire modern picture of space and time, and the man who built that cornerstone imagined himself falling inside a sealed elevator. Einstein once said, "The happiest thought of his life was imagining a man falling freely, feeling no weight at all. He pictured someone inside a sealed elevator plunging downward with the cable cut. Inside that falling box, something magical happens. The person floats. A coin released from their hand hangs in the air beside them. Everything falls together at the same rate, so nothing seems to fall at all. For those few seconds, gravity vanishes from the world inside the elevator. Then Einstein turned the picture inside out. Imagine the same sealed box far out in empty space, with a rocket beneath it firing steadily, dragging it forward. The person inside feels pressed to the floor. A released coin drops to their feet. Standing in that accelerating box feels exactly like standing on the ground." From this he pulled a stunning conclusion. Inside a sealed room, there is no experiment you can perform to tell the difference between sitting still in gravity and accelerating through empty space. The two situations are truly identical. Gravity and acceleration are the same thing wearing different clothes. He named this the equivalence principle, and it became the beating heart of his theory of gravity, general relativity. That theory reshaped our entire understanding of the cosmos. It says gravity is the bending of space and time itself, and that everything moving through that bent space follows the same curved paths, regardless of what it is made of. Light bends, planets orbit, time slows near heavy objects. All of it grows from that one seed. Everything responds to gravity in the same way. General relativity has passed every test thrown at it for over 100 years. It predicted that starlight would bend as it grazed the sun, and it did. It predicted black holes, and we found them. It predicted ripples in space called gravitational waves, and giant detectors caught them shaking the Earth by less than the width of an atomic nucleus. This theory is one of the most successful ideas humans have ever produced, and it rests on the equivalence principle. Everything falls the same. If that principle is true for absolutely everything, then antimatter must fall exactly like matter. No argument, no exceptions. Here is where the stakes explode. If a piece of antimatter fell even slightly differently, if it dropped a touch slower, or drifted the wrong way, it would mean the equivalence principle has a crack in it. And a crack in the equivalence principle is a crack in general relativity itself. The cornerstone of our entire theory of space, time and gravity would be compromised. That is why this experiment carried such weight. Dropping an anti-atom was never a small curiosity. It was a direct challenge to Einstein, a chance to catch the most trusted theory in physics in a mistake, or to confirm it in the one place it had never been checked. For most physicists, betting against Einstein feels like betting against the sunrise. His track record is that good. They fully expected antimatter to fall like everything else, and quietly obey the master. Yet science does not run on expectation. It runs on measurement. And there was a reason, buried in an even deeper symmetry of nature, that gave the confident crowd real ammunition. A theorem so fundamental that it seemed to forbid anti-gravity outright, using nothing but the geometry of matter, time, and mirrors. Beneath everything sits a rule so fundamental that even antimatter itself might be nothing more than ordinary matter seen through a peculiar-looking glass. Physicists call it the CPT theorem, and it braids together three of the deepest symmetries in nature. The first swaps every particle for its antiparticle, turning matter into antimatter. The second reflects the whole world in a mirror, flipping left and right. The third runs time in reverse, playing the film of reality backward. The theorem makes a sweeping claim. If you take any process in nature and apply all 3 flips together. Swap the particles, mirror the space, reverse the clock. The result obeys the exact same laws of physics. This deep symmetry has never once been seen to break. It is woven into the most basic rules that govern reality, so tightly that abandoning it would mean rebuilding physics from scratch. One consequence of this theorem is quietly astonishing. It means that in a real sense an antiparticle behaves like an ordinary particle moving backward through time and space, viewed in a mirror. Antimatter is less a separate substance and more a reflection, a version of matter with several of its properties turned around at once. This ties straight to gravity. The energy content of an antiparticle comes out positive, exactly like ordinary matter. And in Einstein's world, gravity responds to energy. Anything carrying positive energy bends space and gets pulled by other masses in the usual way. Since the CPT theorem forces antimatter to carry positive energy, it should feel gravity as an attraction, falling downward just like its twin. This was the confident crowd's strongest weapon. They could point to CPT and say gravity is not a matter of opinion. The deepest symmetry we know demands that antimatter fall down. To make it fall up, you would have to break a theorem so fundamental that its collapse would shatter far more than one experiment. There were other arguments too, older and cleverer than most people realise. Back in the middle of the last century, physicists showed that anti-gravity in its crudest form leads straight to machines that create energy from nothing, the runaway dancers we met before. Nature guards the rule that energy is conserved with iron discipline. Anything that violates it usually turns out to be impossible, so the case looked closed. A century of confirmed relativity on one side, the unbroken CPT theorem on the other, energy conservation standing guard behind them both. 3 walls, each enormous, all pointing to the same verdict. Antimatter falls down, and anyone hoping otherwise is chasing a fantasy. For a while, that consensus was so strong that testing it seemed almost pointless. Why spend decades and fortunes to confirm what 3 pillars of physics already guarantee? Some scientists openly wondered whether the experiment was worth the trouble at all. The best physicists knew better. Every one of those walls was built on assumptions, and assumptions are exactly what experiments are for. A theorem is only as solid as the ideas underneath it, and history is stuffed with rules that everyone trusted until a careful measurement proved them wrong. And then something remarkable happened. A handful of theorists looked closely at those iron walls and found a hairline gap running through them. A loophole. A way that antimatter might behave strangely without breaking a single sacred law. The door to anti-gravity, seemingly sealed shut, creaked open just wide enough to let a new kind of particle slip through. The walls against anti-gravity looked unbreakable, until a few sharp minds noticed that every one of them had a crack running through the middle. The old arguments, the ones that seemed to forbid antimatter from ever rising, rested on a hidden assumption. They assumed that gravity comes in only one flavour. A single kind of pull, described by Einstein, felt identically by everything. Break the argument down carefully and it forbids that one familiar gravity from ever pushing antimatter away. On that narrow point, the walls held. But what if gravity was not alone? What if, riding quietly alongside the ordinary pull, there was a second force, a faint extra ingredient that no one had ever measured because it was too weak to notice in the ordinary world? A force that treated matter and antimatter differently. 2 physicists working in the deserts of New Mexico dug into this idea with care. They showed that the classic proofs against anti-gravity were narrower than people assumed. Those proofs ruled out pure negative weight, the crude runaway version that breaks energy conservation. They did not rule out a subtler picture. In that picture, antimatter still falls down, still carries positive energy, still obeys the sacred theorems, yet feels a small additional nudge that ordinary matter does not. The trick lies in how energy is counted. The deep theorems guarantee that total energy stays conserved. They say nothing about whether a brand new unknown force might add a gentle, sideways push to certain particles. As long as the books balance in the end, nature permits it. Picture a river carrying 2 identical leaves downstream. The main current is gravity, dragging everything the same way. Now imagine a faint invisible breeze blowing across the water, so weak you would never spot it by watching one leaf. But this breeze only touches leaves of a certain colour. The ordinary leaf drifts straight down the current. The special leaf drifts down too, yet tilts ever so slightly, pushed by a wind no one else can feel. Both obey the river. One feels something extra. That was the loophole. Antimatter could be the special leaf. It would still fall, still honour Einstein and CPT and energy conservation, but a hidden second force might tug it just differently enough to measure. The push could be so small that only the finest experiment ever built could ever detect it. Suddenly the question changed shape. The debate was no longer about crude anti-gravity, the balloon that floats to the ceiling on its own. It became about precision. Does antimatter fall at exactly the same rate as matter, down to the last decimal, or is there a whisper of difference hiding in the details? This reframing lit a fire under the whole field. Confirming that antimatter falls down would no longer settle things. Scientists needed to know how it falls and whether that faint tilt exists. A tiny deviation, a fraction of a percent, would be one of the greatest discoveries in the history of physics, evidence of a new force woven into gravity itself. For that loophole to be real, something had to carry the extra push. Forces in nature do not come from nowhere. Each one rides on a particle, a messenger that darts between objects and delivers the shove or the pull. If a hidden force tilts antimatter, then somewhere out there must be a hidden particle carrying it. And in the late 1970s, a brilliant, restless French physicist gave that particle a name, along with a paper title so bold it dared the whole world to laugh. In 1979, a French physicist published a paper with a title that read like a challenge scrawled on a chalkboard. Anti-gravity, a crazy idea. His name was Joel Shirk, and he was one of the boldest thinkers of his generation, a man unafraid to chase possibilities that made his colleagues wince. Shirk had been exploring some of the most ambitious mathematics in physics, theories that tried to unite gravity with all the other forces of nature into one grand structure. And in the guts of those theories, he found something that made his heart race. The math predicted a new particle, a messenger that would carry a force closely related to gravity, yet with a crucial twist. This particle pulled ordinary matter and pushed antimatter. It was the hidden second force the loophole had demanded, and here it was, falling out of serious equations rather than wishful thinking. Shirk called this particle a graviphoton. The name blends two ideas: gravity, because the particle comes from theories of gravity and couples with roughly gravitational strength, and photon, the particle of light, because the graviphoton behaves in a similar way, carrying a force between objects the way light carries electromagnetism. Here is the magic of it. Ordinary gravity in Einstein's picture always attracts. It has no opposite. But the graviphoton carries a force that can flip its sign depending on what it touches. To a lump of ordinary matter, the graviphoton adds a tiny extra pull, deepening the fall by an amount far too small to notice. To a lump of antimatter, it does the reverse. It pushes. It lifts. It works against gravity. So if the graviphoton is real, antimatter would still fall, dragged down by ordinary gravity, but the graviphoton would fight that fall, shaving off a sliver of the downward pull. Antimatter would drop a touch slower than matter, and in some extreme versions of the idea, if the push were strong enough, it might even cancel the fall entirely, leaving a speck of antimatter to hover or drift upward, exactly the impossible sight scientists had wondered about for decades. Think of two identical sleds sliding down a snowy hill. Gravity pulls both down the slope at the same speed. Now imagine one sled has a tiny hidden fan on its back, blowing gently uphill. It still slides down, because gravity is stronger than the fan, but it slides just a hair slower than its twin. The graviphoton is that hidden fan, and it only switches on for antimatter. Shirk knew how outrageous this sounded. That is why he chose that daring title. He was daring the world to take a serious look at what most people would dismiss as science fiction. He was showing that respected mathematics, followed with care, opened a door toward it. The crazy idea had real equations standing behind it, which is what made it so hard for the field to simply wave away. The physics community reacted with a mix of fascination and deep skepticism. A new force, a new particle, a twist on gravity itself. It was thrilling and unnerving in equal measure. And it raised an obvious demand. If this particle exists, go find it. Show us the antimatter falling slow. The graviphoton did not spring from nowhere. It emerged from one of the most ambitious and beautiful frameworks in all of theoretical physics, a framework that tried to give every particle in nature a hidden partner. To understand where Shirk's crazy particle came from, we have to enter the strange world of supergravity. To see where the graviphoton came from, we have to meet gravity's own messenger, and then imagine giving it a secret family. Every force we know is carried by a particle. Light and electricity ride on the photon. The strong force that binds atomic nuclei rides on particles called gluons. Physicists strongly suspect that gravity too has a messenger, a particle they call the graviton. Nobody has ever caught one, because gravity is so faint that a single graviton is almost impossible to detect. Still, the math practically demands it exists. The graviton is a special kind of particle. Physicists describe particles by a property called spin, a sort of internal twirl. The photon carries a spin of 1. The graviton is predicted to carry a spin of 2, twice as much. That heavier spin is deeply tied to why gravity always attracts and never pushes. A spin 2 messenger produces a force with no opposite, a pure universal pull. Now enter one of the most beautiful and ambitious ideas in physics, called supersymmetry. It proposes that every particle in nature has a hidden partner, a shadow twin with a different spin. The electron has a partner, the photon has a partner, and when you build a version of this idea that includes gravity, the graviton gets partners too. This grander framework is called supergravity, and it is where Shirk's crazy particle lives. In supergravity, the graviton is not a loner. It travels with a small family of related particles, each carrying a different spin, all born from the same underlying structure. Among these partners is a particle with a spin of 1, exactly like the photon. That is the graviphoton. Because it carries spin 1, the graviphoton behaves like light rather than like ordinary gravity, and a spin 1 force has a property that a spin 2 force lacks. It can both push and pull. Like electric charges, where opposites attract and sames repel, a spin 1 force distinguishes between different kinds of matter and can shove some while dragging others. That single fact is the seed of everything strange about the graviphoton. There is another twist that makes the idea even wilder. Several of these theories only work cleanly if the universe has more dimensions than the ones we experience. The math wants extra dimensions beyond our familiar space and time, curled up so tiny we never notice them. And when you fold space in that way, new particles naturally appear, including messengers that behave just like the graviphoton. Gravity leaking through a hidden dimension can look, to us, like a brand new force. Picture a garden hose seen from far away. It looks like a simple line, one-dimensional. Walk closer, and you see it has a second dimension wrapped around it, a hidden loop an ant could crawl along. Extra dimensions work the same way, too small for us to notice, yet real enough to give birth to new particles winding through them. So the graviphoton was not a wild guess pulled from thin air. It emerged from serious attempts to unify gravity with the rest of physics, from supersymmetry, from supergravity, from the geometry of hidden dimensions. Some of the deepest, most respected mathematics in the field kept coughing up this same troublesome particle. That respectability is exactly what made it dangerous to ignore, and the graviphoton was not even the only hidden twin capable of shoving antimatter around. Lurking in the same equations was a second partner, quieter and in some ways stranger, one that could tilt the scales in its own peculiar way. The graviphoton had a sibling hiding in the same equations, a quieter partner that could also reach out and touch antimatter. Physicists call it the graviscala. Where the graviphoton carries a spin of 1, like light, the graviscala carries a spin of 0. It is the plainest possible kind of particle, with no internal twirl at all. Yet that very plainness gives it a strange and important role. A spin 0 force behaves differently from anything in the familiar world. It does not care about charges the way electricity does. Instead, a graviscala produces a force that depends on the sheer amount of stuff in an object, tied closely to mass and energy. It adds a gentle extra tug, a little something on top of ordinary gravity, that could subtly change how fast things fall. On its own, a graviscala would nudge both matter and antimatter. But paired with the graviphoton, the two work together in a delicate dance. The graviscala adds a small pull, the graviphoton adds a pull to matter and a push to antimatter. Combine them, and for ordinary matter the two extra effects can nearly cancel, leaving normal falling almost untouched. That is why we never noticed anything strange dropping apples and hammers for centuries. The hidden forces quietly balance for matter. For antimatter, the balance breaks. The graviphoton flips its sign, so instead of cancelling the graviscalar, it reinforces the difference. The delicate truce that keeps ordinary matter falling normally falls apart the moment you switch to antimatter. The two ghost particles, invisible in our everyday world, would suddenly speak up and change how an antiatom drops. Think of two people carrying a heavy table between them. If they pull with equal strength in opposite directions, the table stays put. That is matter, held in quiet balance. Now imagine one person reverses and pulls the same way. The table lurches. That lurch is antimatter, where the hidden balance breaks and the extra forces add up instead of cancelling. This pairing had a clever advantage that theorists loved. It explained why we had never seen these forces before. If the graviphoton and graviscalar nearly cancel for ordinary matter, then every experiment ever done with normal objects would show perfectly standard gravity, exactly what we observe. The new physics would only reveal itself when you tested antimatter, the one arena nobody had ever probed. The theory hid in the only blind spot we had. There was a catch, and it set the whole hunt in motion. For these forces to matter, the graviphoton and graviscalar could not be too heavy. A heavy messenger produces a force with a tiny reach, dying out over distances far smaller than an atom. A light messenger produces a force that stretches across a room, or a laboratory, or a falling anti-atom. For the graviphoton and graviscalar to change how antimatter falls, they had to be extremely light, their influence reaching across the scale of a real experiment. That single requirement turned a beautiful theory into a concrete target. If these ghost particles were light enough to matter, then their effect on falling antimatter should be measurable. And if you could measure how antimatter falls precisely enough, you could either catch these hidden forces in the act or prove they were too weak to exist. But before anyone could drop a single anti-atom, they had to understand exactly how such a ghostly force would separate matter from antimatter in the first place. And the answer traces all the way down to the beating heart of what a particle truly is. The strangest thing about these ghost particles is how carefully they choose who to touch. They would push antimatter hard and treat you as if you were invisible. To see why, we need to look at what the graviphoton reacts to. Ordinary electricity responds to electric charge. The graviphoton responds to something deeper, a kind of tally of what an object is built from at the most basic level. Count up the fundamental building blocks inside a lump of matter, the quarks and the electrons, and that tally sets how strongly the graviphoton grabs hold. Here is the crucial rule. For ordinary matter, that tally comes out positive. The graviphoton adds its pull in one direction. For antimatter, every one of those building blocks is replaced by its opposite twin, anti-quarks, positrons, and when you flip every building block to its opposite, the tally flips its sign too. The graviphoton now pushes instead of pulls. Same particle, opposite effect, because antimatter is built from opposite parts. This is the heart of it. The graviphoton does not see mass the way gravity does. It sees the difference between matter and antimatter, and it treats the two like enemies. To one it whispers, "Come closer." To the other it whispers, "Go away." There is an elegant detail that makes the whole picture click. Some particles are their own antiparticle. The photon, the particle of light, is identical to its own twin. So is the gluon that binds atomic nuclei. For particles like these, there is no difference between matter and antimatter, so the tally is exactly zero, and the graviphoton ignores them completely. It only responds where there is a genuine difference between a thing and its mirror twin. Now think about what makes up your body: a mountain, an ocean, a star. All of it is ordinary matter, built from ordinary quarks and electrons. To the graviphoton, every one of these is the same, a lump with a positive tally, feeling the same faint extra pull. Since everything around us shares that tally, the graviphoton's effect blends into ordinary gravity. We could never spot it by comparing one everyday object to another, because it treats them all alike. Picture a bouncer at a club who only reacts to a secret badge. Everyone in the ordinary crowd carries the same badge, so the bouncer treats the whole crowd identically, and nobody notices him doing anything special. Then a single person walks in wearing the reverse badge, the mirror image, and suddenly the bouncer shoves them toward the door. Antimatter is that one reversed guest. Only against its opposite does the hidden force finally reveal itself. This is why antimatter was the perfect and only test. Every experiment with matter alone was blind to the graviphoton, because matter is uniform in the eyes of this force. To catch it, you needed to compare matter against its true opposite and watch for the shove. Drop ordinary hydrogen, then drop antihydrogen, and if the two fall at different rates, the ghost has been caught. The logic was airtight. The theory was beautiful. The target was clear. All that remained was the small matter of doing it, of trapping antimatter, cooling it, and dropping it gently enough to watch the faintest force in nature reveal itself. And that, it turned out, was one of the hardest experiments humanity had ever attempted. Before anyone reached that stage, an earlier generation of scientists made a serious run at the graviphoton, using tools that seemed powerful at the time, and walked away with empty hands and a haunting silence. In the 1990s, physicists went hunting for the graviphoton with the best tools they had, and the universe gave them nothing but silence. They could not yet drop antimatter directly, so they searched for the ghost forces in cleverer, more indirect ways. If a graviphoton or graviscaler existed, its faint push would leave fingerprints on how ordinary objects behave, tiny deviations from perfect Newtonian gravity that a sensitive enough instrument might catch. One of their finest weapons was a device called a Torden balance. Picture a small dumbbell hung from a thread so fine that the gentlest force twists it. By placing heavy masses nearby and watching for the faintest twist, scientists could test whether different materials feel gravity in exactly the same way. If a hidden force clung to certain particles more than others, the balance would betray it with a tiny turn. They tested and tested, comparing metal against metal, watching for a whisper of difference. The thread held steady. No ghost appeared. They looked to the heavens as well. Far out in space, pairs of dead stars orbit each other in a furious dance, whipping around at tremendous speeds. One famous pair, discovered decades earlier, spirals so precisely that astronomers can track its motion with astonishing accuracy. If new gravity-like forces existed, they would subtly warp that orbit. Scientists measured the dance for years and compared it to prediction. It matched Einstein's picture to breathtaking precision, leaving no room for a strong new force. From all these efforts, a clear message emerged. If the graviphoton and graviscaler exist at all, their reach must be extremely short, and their strength extremely feeble. The measurements squeezed the ghost forces into a tiny corner. Any push a graviphoton could deliver would have to fade out over a distance of roughly a few feet at most, and be so weak that only the most delicate experiment imaginable could ever hope to see it. For many, this was close to a death sentence for the crazy idea. The theory had promised a measurable force, and every careful search had come up dry. The elegant equations were beautiful, but beauty is not evidence. Nature seemed to be shrugging and saying, "Look all you like, there is nothing here." Yet the searchers had a fatal blind spot, and the sharpest theorists knew it. Every one of those experiments had tested matter against matter. The torsion balances compared one ordinary material to another. The orbiting stars were ordinary matter circling ordinary matter, and we already knew the ghost forces nearly cancel for ordinary matter, hiding themselves in the exact place everyone was looking. Imagine searching a dark house for a burglar, but only ever shining your flashlight into rooms you know are empty. You could search all night and swear the house is clear, while the burglar sits quietly in the one room you never checked. The graviphoton's hiding place was antimatter, and nobody in the 1990s could open that door. So the empty-handed searches did not truly kill the idea. They only sharpened it. They proved that if the ghost existed, it would reveal itself in one place and one place only, the falling of antimatter. The indirect hunt had failed. The direct test had never been attempted, because the technology to trap and drop antimatter simply did not exist yet. The stakes only grew because this quiet question was tangled up with one of the greatest mysteries in the entire universe. A mystery about where nearly all the antimatter has gone. There is a crime scene at the very origin of the universe, and almost all the evidence has vanished. The missing evidence is antimatter. Rewind to the Big Bang, the blazing birth of everything. In those first fractions of a second, the universe was a furnace of pure energy, so hot that particles boiled out of the raw fire. And here is the problem. when energy turns into particles, it does so with perfect fairness. For every particle of matter it creates, it must create one particle of antimatter. They come in matched pairs, always, like coins minted with two faces at once. So the early universe should have been filled with exactly equal amounts of matter and antimatter, every electron balanced by a positron, every quark balanced by an antiquark, a perfectly even split right down the middle. That balance carried a doom inside it. When a particle of matter meets its antimatter twin, they destroy each other completely, vanishing in a flash of pure energy. If the universe truly began with equal parts matter and antimatter, then as it cooled, every particle should have found its twin and annihilated. Everything should have cancelled out, leaving a cosmos of nothing but light. No stars, no planets, no atoms, no you. Yet here we are. The universe is packed with matter and stars and galaxies stretching farther than any telescope can see. Something rescued a sliver of matter from the great annihilation. Somewhere in the chaos, for every billion pairs that destroyed each other, a single extra particle of matter survived with no twin to cancel it. That lonely leftover, one part in a billion, became everything. Every atom in your body is a survivor of that ancient near-total destruction. The question that haunts physics is simple to ask and brutal to answer. Why? Why did matter win? Why is the universe built almost entirely from one side of the mirror, when the fairest possible start should have produced a perfect tie? For a while, one wild idea offered a tantalizing answer, and it connects straight back to falling antimatter. What if matter and antimatter were not truly identical? What if they responded to gravity in different ways? Some thinkers wondered whether anti-gravity might have physically separated the two in the early universe. Perhaps antimatter, pushed by a graviphoton, drifted apart from ordinary matter, sorted into distant regions where we can no longer see it. Maybe the antimatter is out there still, banished to corners of the cosmos beyond our reach, driven away by the very force Shirk had imagined. Picture flour and sugar poured together into a bowl. Normally they mix into an inseparable blur. But imagine one of them was secretly repelled by the bowl itself, floating upward while the other settled down. Given time, they would separate, one gathering at the bottom, the other drifting to the top, until the two were worlds apart. Could gravity have done that to matter and antimatter? It was a thrilling possibility, and it raised the stakes of the drop experiment to the level of cosmic history. If antimatter fell differently, it might explain the greatest disappearance ever, the vanishing of half the universe. To find out, scientists had to stop theorizing and start building. They had to manufacture antimatter with their own hands, hold it captive, and drop it. And the very first obstacle they faced was the same one that had blocked the path for 90 years. Antimatter refuses to sit still. The instant it touches anything ordinary, it destroys itself. Antimatter is the most self-destructive substance in existence. Bring it near anything ordinary, and it detonates into pure energy in an instant. This is the central nightmare of every antimatter experiment. Ordinary matter you can hold in a jar, set on a table, weigh on a scale. Antimatter cannot touch a jar, a table, or a scale, because all of those things are made of ordinary matter, and contact means annihilation. The moment an anti-atom brushes against a wall, it and a piece of the wall vanish together in a burst of energy, leaving nothing behind to study. The reason lies in the most famous equation in science, Einstein's discovery that mass and energy are two forms of the same thing. When matter meets antimatter, their entire mass converts directly into energy, released as a flash of high-energy light called gamma rays. Nothing is wasted. Nothing survives. The conversion is total, the most efficient release of energy nature allows, far beyond anything a nuclear bomb achieves per ounce. That perfect efficiency makes antimatter both wondrous and maddening. A tiny amount holds staggering energy, which is why it fills the dreams of engineers imagining future rockets. But that same trait means you can never let your sample touch its container, ever, or you lose it in a heartbeat. And here is the truly humbling part. We can barely make any of it. Antimatter does not sit in mines waiting to be dug up. Every scrap must be manufactured, one particle at a time, in enormous machines at tremendous cost. If you gathered every bit of antimatter that humanity has ever produced in every laboratory across all of history and let it annihilate at once, The total energy would be barely enough to power a small light bulb for a few minutes. That is the entire global harvest of decades of work. Picture trying to fill a swimming pool using an eyedropper, while the pool has a hole in the bottom that drains it faster than you can add water. That is the antimatter maker's task. You produce it in agonizingly small amounts, and it wants to disappear the instant you make it. Every drop is precious beyond measure, so the problem reached past how to drop antimatter and watch it fall. It was also how to make enough of it to work with, how to hold it without touching it, how to keep it from vanishing long enough to even begin an experiment. For decades, these obstacles felt insurmountable. You cannot weigh how something falls if it explodes the moment you try to handle it. The scientists who took on this challenge needed to invent entirely new ways of holding matter without matter. They needed traps made of nothing but force fields, cages built from magnetism and electricity that could grip antimatter in empty space and never let it touch a solid surface. They needed to freeze it nearly to a standstill, because a fast-moving anti-atom would slam into the walls before any measurement could be made. Building those invisible cages was a triumph of human ingenuity that took years to perfect. But even a perfect cage was not enough on its own, because the simplest kinds of antimatter, the ones easiest to make, carried a fatal flaw for a gravity experiment. They were electrically charged, and that charge would drown the whisper of gravity beneath a roar so loud that falling could never be heard. The easiest antimatter to make is electrically charged, and for measuring gravity, that charge is a catastrophe. The simplest antiparticles are the positron and the antiproton. Both carry electric charge, one positive by convention flipped, one negative. Physicists can produce them, trap them in electric and magnetic fields, and even store them for long stretches. You might think you could just drop one and watch it fall. You cannot, and the reason reveals just how absurdly weak gravity really is. Electric forces are staggeringly stronger than gravity. Not a little stronger. Overwhelmingly, crushingly stronger, by a factor so large it strains the imagination. Between two charged particles, the electric force outmuscles the gravitational force by something like 1,000,000,000,000,000,000,000,000 times over. Gravity, next to electricity, is barely a rumour. For a charged antiparticle, this is fatal to any gravity experiment. The gentle downward tug you want to measure is buried under electric and magnetic forces trillions of times louder. Even the faintest stray electric field, a tiny imbalance of charge on a distant wall, a whisper of static from anywhere in the room, would shove the particle around far more forcefully than gravity ever could. Trying to see the fall would be hopeless. Imagine standing in a stadium during a rock concert, trying to hear a single mosquito buzzing somewhere in the crowd. The music is so loud it shakes your chest. The mosquito is real, and it is making a sound, but you have no chance of hearing it over that wall of noise. Gravity is the mosquito. The electric forces on a charged particle are the roaring concert. No matter how carefully you listen, the whisper is lost. Scientists spent real effort trying to work around this. They dreamed up experiments to fling charged antiparticles through carefully shielded tubes and watch for the tiniest droop as they flew. Every attempt ran into the same wall. Stray electric fields, impossible to fully banish, kicked the particles around thousands of times harder than gravity, smearing out any hope of a clean measurement. The charge always won. The lesson was clear and unforgiving. To measure how antimatter falls, you must strip away the deafening electric noise entirely. And there is only one way to silence electric force completely. You must build something with no overall electric charge at all. Something neutral. An object where the positive and negative charges balance so perfectly that from the outside it feels no electric push whatsoever. For ordinary matter, neutral objects are everywhere. Every atom in your body is electrically neutral, its positive core balanced by its negative electrons. That is why a dropped ball feels only gravity and not a storm of electric shoves. Its charges cancel, and the mosquito can finally be heard. Antimatter needed the same solution. Scientists had to build a neutral atom made entirely of antimatter, with an antimatter core balanced by an antimatter shell, so its charges cancelled, and gravity could finally speak in the quiet. Only then could the whisper of falling rise above the silence. That neutral anti-atom had a name, and creating it became one of the great quests of modern physics. It is the antimatter twin of the simplest atom in the universe, and building even a single one of them would push human ingenuity to its absolute limit. The key to hearing gravity's whisper was to build the simplest possible atom, then build its perfect opposite from scratch. The simplest atom in the universe is hydrogen, a single proton at the centre with a single electron circling it. The proton is positive, the electron is negative, and their charges cancel so cleanly that the whole atom is electrically neutral. Drop a hydrogen atom, and it feels no electric storm, only the faint pull of gravity. Antimatter needed its own version of this. Scientists set out to make antihydrogen. At its heart sits an antiproton, the negatively charged twin of the proton. Circling it is a positron, the positively charged twin of the electron. The negative core and the positive shell balance perfectly, and the whole antiatom becomes electrically neutral, just like ordinary hydrogen. At last, the deafening electric noise falls silent, and gravity has a chance to be heard. Simple to describe, nightmarish to build. To make a single antihydrogen atom, you need two exotic ingredients that both want to destroy themselves, and you have to introduce them gently enough that they join into an atom instead of flying apart or annihilating on the nearest surface. First, you need antiprotons, which are brutally hard to produce and must be captured and stored in invisible traps. Then you need positrons, gathered and cooled and held in their own trap nearby. Then comes the delicate marriage. You have to bring the antiprotons and positrons together softly, coaxing a positron to settle into orbit around an antiproton, forming a bound antiatom, all while keeping every piece from touching a single speck of ordinary matter. Picture trying to introduce two extremely shy, extremely explosive dance partners in a pitch-black room, where the walls are made of dynamite, and any bump means everything blows up. You must guide them toward each other by feel alone, slow enough that they take hands and begin to dance, careful enough that neither one drifts into a wall. Now do it thousands of times to build up enough antiatoms to study. That is the challenge scientists faced, and there is a cruel twist that makes it even harder. To measure gravity, the antiatom must be slow. A fast-moving antiatom would zip across its container and smash into a wall in a fraction of a second, annihilating long before anyone could watch it fall. So the ingredients must be chilled to almost the coldest temperatures in the universe, nearly a complete standstill, so the finished antiatom drifts gently instead of racing to its doom, cold, neutral, and held in a cage of pure force. That was the recipe. Each requirement alone was a monumental task. Together they seemed almost impossible. For years, making antihydrogen at all was a distant dream, and making it cold enough and controlled enough to drop was further still. Yet a determined community of scientists refused to give up. They gathered at one of the most extraordinary machines ever built, a place devoted entirely to the manufacture of antimatter, a factory of the impossible, buried beneath the countryside where two European nations meet, where beams of ordinary matter are smashed apart to conjure their opposites out of raw energy. To hold antimatter, first they had to make it, and to make it they had to slow the fastest, most violent particles in the laboratory down to a gentle crawl. Beneath the border of Switzerland and France sits a machine with a job that sounds like science fiction. It manufactures antimatter to order. This is the great laboratory known as CERN, home to the most powerful particle machines on Earth. And tucked within it is a facility devoted to one strange mission, producing, slowing, and storing antimatter so that experiments can finally get their hands on it. Scientists call this region the Antimatter Factory, and the name fits. Making antiprotons starts with staggering violence. Engineers take ordinary protons, accelerate them to nearly the speed of light, and slam them into a block of metal. The collision is so ferocious that the raw energy of impact converts into a spray of new particles, and among that spray, in tiny numbers, are antiprotons, conjured directly out of energy in keeping with Einstein's famous rule. Matter smashed hard enough gives birth to its own opposite, but these newborn antiprotons come screaming out of the collision at tremendous speed, a chaotic, blazing swarm. At that velocity, they are useless for a delicate experiment. You cannot build a cold, still anti-atom from particles moving at nearly light speed. They would annihilate against the nearest surface in an instant, so the factory's real genius lies not in making antiprotons, but in taming them. The antiprotons are funneled into a series of rings, machines built to do the opposite of what most particle accelerators do. Instead of speeding particles up, these rings slow them down, patiently, stage by stage. One machine catches the wild swarm and gently reins it in. Another cools it further, tightening the herd and draining away its energy. A final, smaller ring slows the antiprotons to a comparative crawl, sapping nearly all their speed until they are calm enough to work with. Think of it like catching rainwater from a raging waterfall. At the top, the water crashes down with unstoppable force, impossible to hold. So you channel it into pool after pool, each one calmer than the last, until at the bottom you have a still, quiet basin you can dip a cup into. The factory does this with antimatter, taming a violent torrent into a gentle trickle you can capture. This slowing process is a marvel of precision engineering. Antiprotons are fragile guests. They must never touch the walls of the rings, so they are steered the entire way by magnetic fields, threaded through vacuum so empty it rivals the space between stars. Any stray wisp of ordinary gas, any contact with a solid surface, and they vanish. Guiding them through mile after mile of machinery without losing them is an achievement that took decades to master. By the end of the journey, the once furious antiprotons drift slowly, cold and calm, ready to be handed off to the experiments waiting to catch them. From a spray of light-speed chaos, the factory delivers a tame, usable supply of antimatter, one of the rarest and most precious substances humans have ever produced. Now the scientists had slow antiprotons. They had positrons cooling in nearby traps. The ingredients for antihydrogen sat ready. All that remained was the most delicate step of all, bringing them together to form a neutral antiatom, and then performing a feat that had defeated physicists for generations, catching that antiatom and holding it still without ever letting it touch a thing. With slow antiprotons and cool positrons finally in hand, scientists faced the moment of truth. Could they coax the two into becoming a single antiatom? The task was exquisitely delicate. An antiproton and a positron do not automatically bond just because they are near each other. The positron has to shed a little energy and settle into orbit around the antiproton, the way an electron settles around a proton to form ordinary hydrogen. Get the conditions slightly wrong, and the particles drift past each other, or worse, wander into a wall and annihilate. Scientists held clouds of antiprotons and clouds of positrons in overlapping invisible traps, cages woven from carefully shaped electric and magnetic fields. Then they gently nudged the two clouds together, letting the particles mingle in a region of empty space, coaxing positrons to fall into orbit around passing antiprotons. Each successful pairing produced a single atom of antihydrogen, a complete anti-atom, neutral and whole, floating in the vacuum. Early on, in the first years of this century, teams managed to produce antihydrogen for the first time. It was a landmark, a genuine piece of antimatter chemistry, the mirror twin of the most common atom in the universe assembled by human hands. Newspapers marvelled, scientists celebrated, yet a painful problem remained, and it stood squarely in the way of any gravity experiment. The first antiatoms were born hot. Even after all the slowing and cooling of their ingredients, the newly formed antihydrogen still carried too much motion. It drifted and darted through the trap at speeds high enough that it would quickly strike the container walls and vanish. And the moment an antiatom becomes neutral, a fresh danger appears. It no longer responds to the electric fields that had been holding its charged ingredients in place. A neutral antiatom slips right through the electric cage, like a ghost passing through bars, and flies off to annihilate. Picture spending months carefully assembling a snowflake, one delicate crystal at a time, only to have it melt the instant it is finished. That was the heartbreak of the early antiatoms. Scientists could make them, but they could not hold them. The finished product escaped or destroyed itself almost as fast as it was born, leaving no time to perform any real measurement, let alone watch one fall. To measure gravity, the antiatoms had to be caught and kept, held still for long enough to release them gently and watch which way they moved, and catching a neutral antiatom is far harder than catching a charged one. With no overall charge to grab, the usual electric cages are useless. Scientists needed a new kind of trap, one that could grip a neutral antiatom through a much fainter handle, using the tiny magnetism buried inside it. This was the next great hurdle. Build a magnetic bottle subtle enough to hold something with no charge, gentle enough not to destroy it, and strong enough to keep it from escaping. For years, it seemed almost out of reach. Neutral antiatoms are slippery, faint and fleeting. Then, after enormous effort, a team finally did it. They built a trap that could catch antihydrogen and hold it, not for a fraction of a second, but long enough to change everything. For the first time in history, scientists had antimatter atoms sitting still in a cage, waiting patiently to be studied. In the year 2010, a team of scientists achieved something that had eluded physics for decades. They caught an atom of antimatter and held it in place. The trick was to build a cage out of pure magnetism, tuned to grip the faintest possible handle. A neutral antiatom has no overall electric charge, so the usual electric cages slide right off it. But the antiatom does have a whisper of magnetism, a tiny magnetic character buried in its structure, like a microscopic compass needle hidden inside. It is an extraordinarily weak handle, but it is a handle nonetheless. Scientists shaped a magnetic field with a very particular form, weakest in the center and stronger all around the edges, forming an invisible valley. An antiatom placed in that valley tends to settle toward the low point in the middle, held loosely in place by its own faint magnetism, gently pushed back whenever it drifts toward the stronger fields at the walls. It was a bottle made of nothing but shaped magnetic force, cradling the antiatom in empty space so it never touched a solid surface. The catch was almost cruelly demanding. This magnetic handle is so weak that only the very slowest, coldest antiatoms can be held at all. A slightly warmer antiatom, moving a touch too fast, simply barrels straight through the magnetic valley and escapes, or slams into a wall and annihilates. So out of every batch of antihydrogen produced, only a tiny fraction were cold enough to be caught. The rest slipped away. Imagine trying to trap a marble by rolling it into a shallow bowl. If the marble moves slowly, it circles the bottom and stays. If it moves too fast, it rolls right up the side and flies out the other end. The magnetic bottle was that shallow bowl, and only the gentlest antiatoms would settle into it. Scientists had to make their antihydrogen colder than almost anything else in the universe, just to have a hope of holding a single one. When they finally succeeded catching and confirming trapped antihydrogen, it was a watershed. For the first time, humanity possessed antimatter atoms held still, floating in a cage, available to be examined at leisure. The mirror twin of hydrogen, the most abundant atom in the cosmos, sat waiting in a laboratory on Earth, captured and secure. This changed everything about what was possible. A trapped anti-atom can be studied. You can shine light on it and read its structure. You can compare it, feature by feature, to ordinary hydrogen, checking whether the mirror world truly matches ours. And crucially, you can release it in a controlled way and watch what it does. A trapped anti-atom is an anti-atom you can finally drop. But catching one anti-atom for a brief moment was only the beginning. To measure something as faint as gravity, scientists needed to hold their antimatter not for an instant, but for a long, patient stretch of time, long enough to steady it, to prepare the delicate release, to give the whisper of gravity the seconds it needed to reveal itself. The question became how long antimatter could be kept caged before it slipped away or died, and the answer, when it came, stunned even the researchers who achieved it. They would hold antimatter not for a flicker, but for a span so long it opened the door to the experiment they had chased for a generation. Catching antimatter was a miracle. Holding it was a marathon. And in the year 2011, scientists shattered every expectation of how long that miracle could last. At first, trapped antihydrogen survived only briefly. A fraction of a second here, a few seconds there. Enough to prove it could be done, far too short to run a careful experiment. Gravity is so faint that watching an anti-atom fall takes real time. A blink of trapping was useless. Scientists needed patience measured not in instants but in minutes. So they pushed their magnetic bottles harder, improving the vacuum, refining the fields, chilling their anti-atoms closer and closer to a total standstill, and they kept extending the clock. Seconds became tens of seconds, tens became hundreds. Then they crossed a threshold that seemed almost unreal. They held a single anti-atom of antimatter trapped and intact for 1,000 seconds. 1,000 seconds is more than 16 minutes. Sit with that. A substance so fragile it explodes at the faintest touch, so rare it must be built one particle at a time, held gently in a cage of pure force for over a quarter of an hour without ever brushing a wall. It is one of the most delicate feats of control humans have ever pulled off, like balancing a soap bubble on a knife edge through a windstorm and keeping it whole for 16 minutes straight. That stretch of time changed the game completely. 16 minutes is an eternity in the world of particle physics. It is long enough to steady the anti-atom, to prepare a careful release, to give the whisper of gravity room to speak. With antimatter that could be held that long, the dream of dropping it and watching it fall finally moved from fantasy into engineering. During those long trapping times, scientists did more than simply hold their prize. They began to study it. They shone precisely tuned light on trapped antihydrogen and read back its structure, comparing it to ordinary hydrogen with growing precision. Feature after feature, the anti-atom matched its ordinary twin, confirming that the mirror world looked astonishingly like our own in nearly every way tested. The symmetry between matter and antimatter held, at least in the ways light could probe. Yet one property stayed stubbornly out of reach through all of this: gravity. Reading an antiatom structure with light does not tell you which way it falls. To answer that, the trapped antiatoms had to be released in their motion tracked up or down as the cage let go. Studying antimatter while holding it still was a triumph. Watching it move under gravity was a different and harder challenge. The pieces were finally assembling. Scientists could make antihydrogen. They could catch it. They could hold it for 16 minutes. They could cool it to a near standstill. Every ingredient the gravity experiment demanded was at last within reach. After 90 years of the question hanging unanswered, the tools to answer it directly had been forged. But one deep obstacle remained, woven into the very nature of the trap itself. The magnetic bottle that held the anti-atom so carefully was also the thing standing between scientists and the answer, because the magnetic forces cradling the antimatter were vastly stronger than the faint gravity they wanted to measure. To see the fall, they would have to fight against their own trap, and the balancing act required was almost unimaginably precise. Here was the cruel irony at the heart of the experiment. The magnetic cage that held the antimatter so gently was itself a hurricane, drowning out the very whisper scientists wanted to hear. Remember how faint gravity is. It is the weakest force in nature by an enormous margin, and the magnetic forces holding the anti-atom in its bottle were, by comparison, overwhelmingly strong. They had to be, to grip something as slippery as a neutral anti-atom at all. So while the anti-atom sat trapped, gravity tugged on it faintly, and the magnetic forces shoved it around far more powerfully, burying that faint tug completely. As long as the trap was fully on, watching gravity was hopeless. It would be like trying to feel a feather land on your shoulder during an earthquake. The feather has real weight, but the ground heaves so violently you never notice. The magnetic forces were the earthquake. Gravity was the feather. So scientists faced a delicate problem. To see the anti-atom fall, they had to weaken the trap, easing off the magnetic forces until they finally dropped low enough for gravity to matter. But weaken the trap too much, or unevenly, and the anti-atom would escape in some random direction that had nothing to do with gravity, ruined by the very fields meant to release it. The balance had to be extraordinary. They needed the magnetic forces at the top and bottom of the cage matched with breathtaking precision. If the fields were even slightly stronger on one side, magnetism would push the anti-atom that way instead of gravity, ruining the measurement. Picture a scale so sensitive that a single grain of dust on one pan would tip it. Now imagine you must balance the two pans against each other perfectly, so that when you finally release your sample, only gravity decides which way it goes. That was the level of control required. To make this work, scientists conceived a clever design. They would tune the magnetic barriers at the top and bottom of the trap independently, dialing them up and down like two carefully matched gates. By balancing those gates against each other, they could create a moment where the magnetic push-up and the magnetic push-down cancelled almost perfectly. In that finely balanced instant, the only thing left to tip the anti-atom one way or the other would be the faint, patient pull of gravity. This was the key insight that made the whole experiment possible. Do not try to shut off the enormous magnetic forces entirely, which would release the anti-atom chaotically. Instead, balance them against each other so precisely that they neutralize, leaving gravity as the deciding vote in a nearly tied election. The anti-atom poised at the balance point would then drift the way gravity nudged it, up or down, and reveal at last which way antimatter falls. To pull this off, the trap needed a special shape. Most traps are built like short, squat bottles, with no clear up or down. This experiment demanded something different. A tall, vertical chamber, standing upright like an elevator shaft so that up and down were clearly defined, and an anti-atom released at the balance point would have a clear path to fall along, either climbing toward the top or sinking toward the bottom. They built exactly that. A towering vertical trap engineered for one purpose, to drop antimatter and watch which way it went. And giving that tower a name, they turned decades of dreaming into a machine ready to answer the oldest unanswered question about antimatter. To finally drop antimatter, scientists built a machine unlike any before it. A tall vertical tower standing on its end like an elevator shaft for anti-atoms. Earlier traps had been squat and horizontal, fine for holding antimatter but useless for measuring which way it fell, because they had no clear up or down. The new machine turned the whole idea upright. It was a tall cylindrical chamber, standing vertically, with the magnetic trap stretched along its height. At the very top, a magnetic gate. At the very bottom, another. Between them, the region where anti-atoms would be held and then released to rise or sink. This vertical design was the crucial change. In a tall standing tube, up and down finally means something clear. An anti-atom released at the balance point in the middle has two possible fates: climb toward the top gate or fall toward the bottom gate. By watching which way it went, scientists could read the answer directly. The whole apparatus was essentially a giant, exquisitely sensitive scale, built to weigh which direction antimatter drifts. The engineering behind it was staggering. The magnetic fields along the tower had to be shaped and controlled with extreme care, so the top and bottom gates could be tuned independently and balanced against each other. The vacuum inside had to be among the emptiest environments ever created, emptier than the space between planets, so no stray wisp of ordinary gas would destroy the precious anti-atoms before the measurement. And detectors surrounded the tower, watching every inch, ready to catch the flash whenever an anti-atom met its end against a wall. Think of the tower as a courtroom built for a single trial that had waited 90 years for its day. The antimatter is the witness, and it can only give its testimony once, in the instant it is released. Everything in the courtroom, the balanced gates, the vacuum, the detectors, exists to make sure that when the witness speaks, its answer is clear and honest, decided by gravity alone. Balancing the two gates was the heart of the method. Scientists would set the top and bottom magnetic barriers to carefully chosen strengths, then compare what happened as they varied that balance. If the barriers were tuned so the top and bottom pushed equally, then in that balanced state gravity would be the deciding factor. Anti-atoms would tend to spill out the bottom, pull down, if antimatter falls the way matter does. If antimatter rose instead, they would spill out the top. The direction of the spill was the answer. To rule out mistakes, the plan was to repeat the release many times, shifting the balance of the gates in careful steps, mapping out exactly how the anti-atoms behaved across a whole range of settings. A single measurement could be a fluke. A dozen, each pointing the same way, would be a verdict. Scientists demanded that rigor because the question was too important for a lucky guess. Every piece was now in place. The factory made the antimatter. The traps caught it. The cold held it still. The tower stood ready, gates balanced, detectors watching, vacuum pristine. After a century of theory, argument, and impossible engineering, the moment had arrived to do it at last. To take a cloud of antihydrogen, hold it in the balanced heart of the tower and let it go. What happened next would settle a question older than most of the scientists in the room, and either confirm Einstein one more time or crack the universe open in a way no one was ready for. The moment finally came. A cloud of antihydrogen sat trapped in the balanced heart of the tower, and scientists prepared to let it go. The procedure was a masterpiece of patience. First, the anti-atoms had to be as cold and still as possible, drifting rather than racing, so that when released they would respond to gravity's gentle pull instead of their own wild motion. Then the two magnetic gates, top and bottom, were tuned to the chosen balance, and then, slowly and carefully, scientists began to lower the strength of those gates, easing the magnetic grip that had held the antimatter in place. This was the delicate part. Lower the gates too fast or unevenly, and the anti-atoms would be flung out by magnetism, their motion decided by the trap rather than gravity. So the release was done gradually. The magnetic barriers eased down in a smooth, controlled way, weakening the cage bit by bit until the faint pull of gravity could finally tip the balance. As the trap opened, the anti-atoms began to escape, and here the whole experiment came down to a single question. As each anti-atom slipped free of the weakening cage, which way did it go? Did it drift downward, sinking toward the bottom gate, pulled by the earth like every ordinary thing that has ever fallen? Or did it climb upward, defying gravity, drawn toward the top in a way that would rewrite physics? There was no way to watch an anti-atom directly. It is far too small and faint, but there was a way to know where it ended up, and it was beautifully simple. Wherever the anti-atom finally touched the wall of the tower, it annihilated, converting itself into a flash of energy. If it drifted down and struck the bottom, the flash came from below. If it rose and struck the top, the flash came from above. The direction of the flash revealed the direction of the fall. Picture standing in a completely dark room with a ball that glows for only an instant when it hits the floor or the ceiling. You cannot see the ball fly, but you can see the flash when it lands, and from where that flash appears, you know instantly whether it went up or down. That was the elegant heart of the method. The anti-atoms announced their fate in a burst of light at the moment of their destruction. Surrounding the tower stood banks of sensitive detectors, watching every inch of the chamber, ready to catch each flash and record exactly where it came from. Every escaping anti-atom would leave one final signal, a pinpoint of light marking whether it had sunk or soared. Count enough of those flashes, note whether they clustered near the top or the bottom, and the answer to a 90-year-old question would emerge from the tally. The tension in the experiment was immense. Most scientists expected the flashes to gather at the bottom, confirming that antimatter falls down like everything else. But expecting an answer is not the same as knowing it. Until the anti-atoms were released and the flashes counted, the possibility remained, however faint, that antimatter would do something no one had ever seen, that it would rise. So they ran the experiment. They released the anti-atoms again and again, shifting the balance of the gates in careful steps, watching for the flashes and recording where each one bloomed in the dark. Slowly, measurement by measurement, a pattern began to take shape in the data. A clear and unmistakable answer, written in bursts of annihilation light. Each anti-atom died in a tiny flash of light, and those flashes became the scoreboard for the oldest question in antimatter physics. The idea was simple enough to explain to a child. Release the anti-atoms from the balanced trap, then watch where they hit. An anti-atom that fell downward would strike the lower part of the tower and annihilate there, producing a burst of energy at the bottom. An anti-atom that somehow rose would strike the upper part and flash near the top. By tallying up how many flashes appeared below versus above, scientists could read off which way antimatter tended to go. The detectors surrounding the tower were built to catch exactly this. When an anti-atom annihilates, it does not vanish quietly. It erupts into a spray of particles and energy, a distinctive signature that sensitive instruments can detect and pinpoint. From that signature, scientists could reconstruct where along the tower the annihilation happened, marking each event as an upflash or a downflash with real confidence. They released the anti-atoms in carefully controlled runs, and the detectors lit up with events, each one a tiny death, each one a data point. A flash here, low in the tower, a flash there, also low, occasionally a flash near the top. The scientists gathered these events patiently, building a record of where the antimatter chose to go once gravity had its say. To make the answer trustworthy, they did not rely on a single run. They repeated the release many times, and crucially, they varied the balance of the top and bottom magnetic gates across those runs. By deliberately biasing the trap slightly upward or downward in a known way, they could check that the anti-atoms responded exactly as physics predicted, ruling out hidden errors in their fields or their detectors. If the antimatter behaved sensibly under every setting, the final answer could be trusted. Think of it like weighing something on a scale. then deliberately adding known weights to one side and the other, checking that the needle moves exactly as it should each time. Only when the scale passes every one of those checks do you trust the final reading. The scientist put their tower through the same gauntlet, testing it against many balance points, making sure it told the truth. As the runs accumulated, the pattern in the flashes grew clearer and clearer. When the magnetic gates were balanced so that only gravity should decide, the flashes did not scatter randomly half up and half down. They leaned strongly. The great majority of anti-atoms were ending their lives in the lower part of the tower, striking below the balance point far more often than above it. The antimatter was sinking. Run after run, the flashes clustered toward the bottom, exactly as they would for a cloud of ordinary hydrogen released the same way. The scoreboard of annihilation light was telling a consistent story, written in burst after burst of energy, and the story pointed downward. But science demands more than a leaning pattern. It demands numbers, a clear measurement of how strongly the anti-atoms fell, and whether that matched the pull of ordinary gravity. The scientists took their thousands of flashes and turned them into a hard result, a definitive answer to the question that had waited since Dirac first dreamed antimatter into being. And when they announced what the flashes revealed, it echoed around the world, closing one chapter of physics and quietly opening another. In the autumn of 2023, scientists announced the answer to a question that had waited nearly a century. Antimatter falls down. The result came from that towering trap, from thousands of anti-atoms released and tracked by their dying flashes. When the magnetic gates were balanced so that gravity alone decided, roughly 8 out of every 10 anti-atoms sank toward the bottom of the tower and annihilated there. The rest went up for reasons we'll come to, but the great majority fell, exactly as a cloud of ordinary hydrogen would under the same conditions. The scientists compared their results directly to what ordinary matter would do. They asked a simple question. If we had released normal hydrogen instead of antihydrogen, balanced the same way, how would it have behaved? The answer was that the antimatter behaved the same. Within the precision of the experiment, antihydrogen fell downward with the ordinary pull of Earth's gravity, the same acceleration that governs a dropped stone or a falling raindrop. For the first time in history, humanity had directly watched antimatter respond to gravity, and it responded like everything else. It fell. The crude dream of anti-gravity, the vision of a speck of antimatter floating up toward the ceiling on its own, was dead. Antihydrogen does not rise. It sinks, pulled toward the Earth like its ordinary twin. The news travelled around the world. It confirmed what most physicists had long expected, and confirmed it in the one place the assumption had never been tested. Einstein's equivalence principle, the idea that everything falls the same regardless of what it's made of, passed a test it had never faced before, using the most exotic substance in the laboratory. The cornerstone held. General relativity survived another challenge, extended now to antimatter itself. Consider the sheer scale of this achievement. A question first whispered when antimatter was still just a strange solution in Dirac's equation, argued over for generations, blocked for decades by the near impossibility of the experiment, had finally been answered with a direct measurement. Scientists made antimatter, cooled it, caged it, balanced it, released it, and watched it fall, all to satisfy the simplest curiosity a child could have. Which way does it drop? There was a quiet beauty in the outcome. Antimatter, for all its strangeness, its flipped charges, its self-destruction, its role as matter's mirror twin, obeys the same gravity as the rest of us. It falls with us. It belongs to the same universe, governed by the same pull. In the one respect that had remained unknown, the mirror world matched our own. And yet, this was not the end of the story, because the experiment, for all its triumph, was still a first attempt, and its precision was limited. It could say clearly that antimatter falls down, and roughly how fast. It could not yet say whether antimatter falls at exactly the same rate as matter, down to the finest fraction, and that fraction is where the graviphoton might still be hiding. The crude anti-gravity was gone. The subtle question remained wide open. Somewhere in the last decimal places, a faint difference might still lurk, A whisper of Shirk's crazy particle too small for this first experiment to catch. But before we chase that whisper, there is a puzzle in the result worth pausing on. Not every anti-atom fell. A stubborn fraction flew upward, and understanding why reveals something important about how close this measurement came to its limit. Here is a detail that could confuse anyone. If antimatter falls down, why did a fraction of the anti-atoms fly up toward the top of the tower? At first glance it sounds like a contradiction. The whole point was that antimatter sinks, so shouldn't every last anti-atom have dropped to the bottom? The answer reveals something crucial about the experiment, and it has nothing to do with anti-gravity. The anti-atoms that rose were not defying gravity, they were carrying leftover heat. Remember that these anti-atoms, cold as they were not perfectly still. Cooling something to near a standstill is not the same as freezing it into absolute stillness. The anti-atom still jiggled, still drifted, still carried a tiny bit of random motion, the way a barely simmering pot of water still has faint swirls even before it boils. That leftover motion is what physicists call heat, and even a whisper of it matters when gravity's pull is so faint. So when the trap opened, most anti-atoms drifted downward under gravity, but some happened, at that instant, to be moving upward with just enough speed to climb toward the top gate before gravity could turn them around. They shot up because they were already coasting that way, carrying leftover motion, like a ball tossed gently upward that rises for a moment before falling back. Some of those upward coasting anti-atoms reached the top wall and annihilated there before gravity could reclaim them. This is exactly why roughly 2 out of every 10 flashes appeared near the top rather than the bottom. Those were the anti-atoms whose leftover motion sent them upward faster than gravity could pull them down in the brief moment before they hit a wall. The remaining 8 out of 10, drifting more slowly or already heading down, sank as expected. The overall lean was clearly downward, but the leftover heat blurred the picture, sending a minority the other way. Picture releasing a swarm of gnats inside a tall jar and gently blowing downward on them. Most drift toward the bottom, but a few energetic ones, already flying upward when you started, reach the top before your breeze can push them down. Watching the swarm, you would still see clearly that the overall drift is downward, even though some gnats went up. The anti-atoms were that swarm, and gravity was the gentle downward breeze. This leftover motion was the great enemy of precision. It smeared the result, adding a fog of randomness on top of gravity's gentle pull. The colder the anti-atoms, the less this fog, and the sharper the measurement. To see gravity clearly, scientists want their antimatter as motionless as physically possible, so that almost every anti-atom obeys gravity alone with as little random wandering as they can manage. And this points straight to the limit of the first experiment. Its precision was capped in part by how cold the anti-atoms could be made. The heat that sent some anti-atoms upward also blurred the exact value of how fast antimatter falls. The experiment could say confidently that antimatter sinks with roughly the ordinary pull of gravity. It could not yet pin that pull down to the fine precision needed to hunt for Shirk's ghostly particle. To catch a whisper as faint as the graviphoton, scientists would need to push far beyond this first result, into a realm of precision where even the tiniest deviation between matter and antimatter could finally be seen or ruled out. And that meant reckoning with just how rough this historic first measurement really was. The first measurement answered the big question, and left a bigger one wide open. It proved antimatter falls down. It could not yet prove antimatter falls at exactly the same rate as matter. The precision of that first result was modest by the standards of physics. Scientists could say that antihydrogen falls downward, pulled by Earth's gravity, at a rate roughly matching ordinary matter, give or take a fairly wide margin. The measurement pinned the fall to somewhere in the neighbourhood of ordinary gravity, but with enough uncertainty that a real difference could still be hiding inside that margin. It was a sledgehammer answer to a question that eventually needs a scalpel. That distinction matters enormously, because the interesting physics lives in the fine details. Crude anti-gravity, antimatter floating up on its own, is dead. That would have been a huge, obvious effect, and the experiment ruled it out cleanly. But the graviphoton was never expected to produce a huge effect. Its whisper would show up as a tiny difference, antimatter falling a fraction of a percent slower than matter, or that same fraction faster. A difference far too small for this first experiment to detect. So the current situation is a strange kind of victory. Scientists have closed the door on the wildest possibility and confirmed Einstein in a brand new arena. But the subtle door, the one that Shirk's particle could slip through, remains open. To either catch the graviphoton or slam that door shut too, they need to measure how antimatter falls not roughly, but exquisitely, down to a tiny fraction of gravity's strength. Imagine you want to know whether two runners finish a race at the same time. A first crude measurement tells you they both finished within the same minute. Good to know, but useless if the difference you care about is a few thousandths of a second. To catch that, you need a far better stopwatch, one that can split time finely enough to reveal a gap invisible to the naked eye. The gravity experiment is at the same crossroads. It has the crude stopwatch. It needs the precise one. Reaching that precision is the next great challenge, and it demands pushing every part of the experiment further. Colder antiatoms, so leftover heat no longer blurs the result. More antiatoms, so the statistics sharpen. Better balanced traps, so the magnetic forces cancel even more perfectly. Every improvement squeezes the uncertainty smaller, bringing scientists closer to the fine measurement where a graviphoton would finally reveal itself or prove too faint to exist. The prize is worth the effort. A precise measurement showing antimatter falls exactly like matter would be a stunning confirmation of the deepest symmetries in physics, closing off decades of speculation. But a precise measurement showing even a tiny difference would be revolutionary. Direct evidence of a new force woven into gravity, a discovery worthy of the highest honours in science, and a rewriting of the textbooks. This is why the first experiment, for all its glory, was really a beginning. It opened the door to a new kind of physics, the precision study of how antimatter feels gravity. And the same team was not alone in the chase. Around the antimatter factory, rival experiments were rising, each with its own bold strategy for measuring the fall of antimatter more precisely than ever before. One of them planned to skip the crude drop entirely, and instead build a single antiatom so cold, so perfectly controlled, that its fall could be timed with almost unimaginable accuracy. One rival experiment chose a path so audacious it almost sounds backward. To drop a neutral antiatom perfectly, they would first give it an electric charge on purpose. The logic is clever. We saw that charged antimatter is useless for measuring gravity because electric forces drown out the pull. But charge also gives you a handle. Charged particles can be grabbed, steered, and above all cooled by electric fields with extraordinary control, chilled to temperatures far colder than a neutral antiatom can easily reach. And cold is everything for precision, because leftover heat is what blurs the fall. So this experiment planned a two-step trick. First, build a special version of antihydrogen carrying an extra positron, giving the whole antiatom a net positive charge. This charged antiatom can then be held and cooled with exquisite electric control, chilled to a temperature so low it is nearly at the absolute limit of stillness, far colder and calmer than any neutral antiatom drop before. Then, at the last possible moment, comes the magic. Using a precisely aimed pulse of laser light, scientists strip away that extra positron, instantly turning the charged antiatom back into an ordinary neutral one. In that instant, the electric handle vanishes, the deafening electric forces switch off, and the now neutral antiatom is left almost perfectly still, floating free, feeling nothing but gravity. And then they let it fall, timing its descent with tremendous precision. The beauty of this approach is that it defeats the problem of leftover heat. Because the antiatom was cooled while charged, using the powerful tools that only work on charged particles, it starts its fall far stiller than anything the first experiment could manage. With almost no random motion to blur the result, its descent reveals gravity's pull with far greater sharpness. Instead of a swarm of jiggling antiatoms leaning downward, you get a single, nearly motionless antiatom whose fall can be clocked with care. Picture the difference between trying to time a feather dropped in a breezy room and timing a steel ball dropped in perfectly still air. The feather flutters and drifts and your measurement is fuzzy. The ball falls clean and straight, and you can time it precisely. This experiment aims to turn the fluttering antiatom into that clean, straight fall by chilling away nearly all its random motion before letting go. The technical demands are staggering. building an anti-atom with an extra positron, cooling it to a near absolute standstill, stripping the positron at exactly the right instant with a laser, and then measuring the faint fall of a single neutral anti-atom, all without letting it touch a wall, is a symphony of precision at the very edge of what technology allows. Each step alone is a formidable achievement. Chaining them together borders on the miraculous. If it works, this method could measure how antimatter falls with a precision far beyond the first crude result, sharp enough to begin hunting seriously for any tiny difference between matter and antimatter. It could push the search for the graviophoton into new territory, either narrowing its hiding place dramatically or, in the most thrilling scenario, catching the first faint sign of it. This ultra-cold drop is one of several strategies now converging on the same goal, and each one attacks the measurement from a different angle. Another experiment refused to trap or drop anything at all. Instead, it planned to send a beam of antimatter flying sideways and measure its fall the way you might read the drift of a shadow. A third experiment took a completely different route. It would not trap the antimatter, nor drop it straight down. It would fire a beam of antiatoms sideways and measure how far they sagged in flight. The idea borrows from something familiar. Throw a ball horizontally, and even as it flies forward, it slowly falls, curving toward the ground. The faster it flies, the less it drops over a given distance, but it always sags a little. Measure that sag precisely, and you learn how strongly gravity pulled on the ball during its flight. This experiment aims to do exactly that with a beam of antimatter, measuring the tiny downward droop of antiatoms as they streak across the laboratory. The trouble is that the sag is minuscule. Antiatoms in the beam move quickly, and gravity is so faint that over a short flight they fall by an almost immeasurably small amount, far less than the width of a hair. To detect such a tiny droop, scientists needed a ruler of extraordinary finesse, something that could measure a vanishingly small vertical shift in a fast-moving invisible beam. Their solution is a beautiful piece of physics. They send the beam through a series of finely spaced gratings, like passing light through a picket fence with incredibly narrow gaps. As the antiatoms pass through these gratings, they cast a striped pattern of shadows on a detector at the far end. And here is the trick. If the antiatoms fall even slightly during their flight, the entire striped pattern shifts downward by a matching amount. By measuring how far the pattern of stripes has slid, scientists can read off how far the antiatoms fell, even when that fall is far too small to see directly. It is a way of turning a tiny, invisible droop into a visible shift in a pattern, amplifying the faint signature of gravity into something measurable. The stripes act like the hands of an ultra-sensitive clock, and their displacement tells the story of the fall. Imagine measuring how much a distant tightrope walker dips in the middle of the wire too far to see directly. Now imagine the walker casts a striped shadow on the ground through a slatted fence, and you watch that shadow instead. A tiny dip in the walker shifts the whole shadow, and by measuring that shift you learn the dip. The grating method does this with beams of antimatter, reading their fall through the sliding of shadows. This shadow reading approach has its own advantages. It works with a flowing beam instead of a single trapped antiatom, which is easier to produce steadily, and it offers a completely independent way of measuring antimatter's fall, using different tools and different assumptions than the drop experiments. That independence is precious, because when several very different methods all agree, scientists can be far more confident the answer is real. Together, these experiments form a converging assault on the same question. One balances antiatoms in a tower and watches them sink. One chills a charged antiatom to a near standstill and drops it clean. One fires a beam sideways and reads the sag in a pattern of shadows. Each attacks from a different direction, and each pushes the precision higher, closing in on the fine measurement that could finally reveal whether antimatter falls exactly like matter, or whether Shirk's ghost is hiding in the decimals. And that is where the real prize waits, in the tiniest gap between matter and antimatter, a gap that could crack open the deepest secrets in all of physics. The wild dream of antimatter floating upward is dead, and yet the deepest treasure in this entire story still lies buried, waiting in the tiniest sliver of a difference. The precision hunt matters for deep reasons. Confirming that antimatter falls down was the headline, but scientists were always chasing something more subtle underneath. They want to know whether antimatter falls at exactly the same rate as matter, matched to a hair, or whether there is a faint difference hiding in the fine details. Because that faint difference, if it exists, would be a doorway into physics beyond anything we currently understand. Recall Shirk's graviphoton and its quiet partner, the graviscalar, the ghost particles that would pull matter and push antimatter. If they are real and light enough, they would make antimatter fall a tiny fraction slower than matter, a difference of perhaps a fraction of a percent. That is precisely the kind of whisper the new precision experiments are built to hear. Catch antimatter falling even slightly differently, and you have caught direct evidence of a brand new force woven alongside gravity, a discovery that would shake physics to its foundations. The implications reach into the deepest questions we have. A new gravity-like force would be a crack in Einstein's equivalence principle, the sacred rule that everything falls the same. It could be a signpost toward the long-sought unification of gravity with the other forces, a hint of the extra dimensions or hidden symmetries that theories like supergravity predict. It might even connect to the mystery of what fills the universe, since some versions of these ghost particles have been linked to the strange energy that drives the cosmos to expand ever faster. And it would speak, at last, to the greatest disappearance of all, the vanished antimatter of the early universe. If matter and antimatter respond even slightly differently to gravity, that difference might be a thread leading toward why the two were not perfectly equal in the first place, why matter won and antimatter nearly vanished. A tiny gap measured in a laboratory could echo all the way back to the first fractions of a second after the Big Bang. Picture a detective who has spent a lifetime on a cold case, finally holding a single strand of hair from the scene. To the eye it looks like nothing, but under a powerful enough microscope that one strand could reveal everything, the solution to the whole mystery. The tiny difference in how antimatter falls is that strand of hair. Crude tools see nothing in it. The finest tools might see a universe of new physics. That is why scientists keep pushing chilling anti-atoms colder, balancing traps finer, reading shadows sharper. They already know antimatter falls down. They are hunting for the whisper of difference that could rewrite our understanding of gravity, of forces, of the birth of the cosmos itself. Every improvement in precision brings them closer to either hearing that whisper or proving, once and for all, that it is silent. The search is only beginning. The first crude answer arrived recently, and the precision experiments are still being perfected, still gathering their first sharp data. In the coming years, they will push the measurement further than anyone has ever managed, into the realm where Shirk's crazy idea finally lives or dies. And whatever they find, the answer will carry a strange and humbling truth about our place in the universe, about the antimatter that falls beside us, and about the missing half of creation that gravity, in the end, could not explain away. After 90 years of wonder, the verdict is in, and it carries a quiet beauty that ties this whole story together. Antimatter falls with us. The great experiment settled the oldest question about antimatter's weight. Release a cloud of antihydrogen, and it sinks toward the Earth, pulled by the same gravity that holds you in your chair, drops a raindrop and swings the moon around the sky. The mirror twin of ordinary matter, for all its flipped charges and self-destruction and strangeness, obeys the same fundamental pull. In the one respect that had remained a total blank for nearly a century, the mirror world matches our own. There is something profound in that. Antimatter is the great rebel of physics, opposite in nearly every way we can measure. Yet gravity does not care about the rebellion. To gravity, matter and antimatter are the same, both drawn together, both falling as one. In the deepest sense, antimatter belongs to our universe, governed by the same law that governs everything else. It falls beside us, part of the same cosmic family. And yet the story leaves us with a haunting question still unanswered. If antimatter falls exactly like matter, then gravity did not banish it. It did not push the antimatter away to some distant corner of the cosmos in the early universe. The tantalizing idea that anti-gravity might explain the greatest disappearance in history is gone. Whatever erased almost all the antimatter from creation, it was not gravity separating the two. So the mystery of the missing antimatter grows deeper, not shallower. We are still here, built from the one part in a billion of matter that survived the Great Annihilation, and we still do not fully know why. Gravity has been ruled out as the culprit, and the search for the true explanation continues, in different experiments probing different forces, hunting for the subtle imbalance that tipped the scales toward matter and gave rise to everything. But the precision hunt for how antimatter falls is only beginning, and it still holds one last thrilling possibility. Somewhere in the fine details, in a difference too small for the first experiment to catch, Shirk's ghostly particle might still be hiding. If the coming experiments, chilling anti-atoms to a near standstill, reading the sag of beams through sliding shadows, ever catch antimatter falling a whisper differently from matter, it would crack open a new realm of physics, a hidden force, a doorway to unification, a clue to the birth of the cosmos. Think of what this whole journey represents. Humans took a substance that exists nowhere around us, conjured it out of pure energy in a factory of the impossible, caught it in cages of invisible force, cooled it to the edge of stillness and dropped it, all to answer a question a child could ask. Which way does it fall? That we can even attempt such a thing is a testament to how far curiosity and ingenuity can carry us. The next time you drop something and watch it fall, remember that far beneath a mountain on the border of two nations, scientists dropped the opposite of ordinary matter and watched it fall too. The universe, in that moment, revealed a little more of itself. Antimatter falls with us, and in the tiny gap where it might not fall quite the same, the next great secret of physics may still be waiting to be found.